Well, our magical journey through Chapter 5 continues with 5.4 logarithmic functions. So we've been discussing what are called exponential functions, and now we have a whole new thing coming in, but we'll see what the relationship is. Specifically, there's a way to change an exponential statement to a logarithmic statement. And then, just like we can evaluate exponential functions and solve them, we'll learn how to do those with logarithmic functions. That's basically what we want to do here, understand what logarithms are and how they relate to exponential functions, and then solve equations using them. So, the way we talk about logarithms is they have a base. Hey, so did exponential functions. That base has to be positive and can't be 1, which is the same restriction we put on bases of exponential functions. And we write it as log subscript a x, and you say this, the logarithm with base a of x. Frequently the word with is just sort of omitted in speaking, and you say the logarithm base a of x. Okay. And the relationship between this is y equals log base a of x is exactly the same as saying x equals a to the y. Okay. So y is log base a of x means exactly the same as x equals a to the y. So what's the domain of a log function? To put it in here, I must have gotten it out here. A to the y would have to equal x. But what's the range of an exponential function? Positive numbers. So the domain of any log function is the range of the corresponding exponential, which is positive numbers. Now, what else did we discuss a couple sections ago where the domain of something becomes the range of something else and vice versa? Inverse functions. That's what this is. It's the inverse function of an exponential. So let's see why that is. Suppose I had y equals a to the x, a nice exponential function. It's 1 to 1 because it's an increasing. Let's just say a is bigger than 1. It's increasing, so it's 1 to 1. It has an inverse. What is the inverse? Well, I switch it and I say x equals a to the y. And now I try to solve for y, but we really don't have tools for doing that. That's what this is. The logarithm base a is exactly the tool that says if I need to solve this for y, I just by definition say y is the logarithm base a of x, and I call it a day. I know the inverse exists, but we lacked a tool to express it somehow, so we're inventing it. Logarithms are the inverses of exponentials. Okay, the log base a is the inverse function of the exponential of base a. So for example, if y is the log base 7 of x, and to convert this into an exponential, I would say x is 7 to the y. So 7 squared is 49, so 2 is log base 7 of 49. If y is log base 4 of x, then 4 to the y is x. For example, y is negative 1 equal to log base 4 of a quarter because 4 to the negative 1 equals 1 quarter. So try to change each of the following into an equivalent logarithmic statement. They're written as exponential statements right now. Identify what the base is. Okay, whatever your base is, you're going to have log base that of something equals something else. Sorry, not 0. I meant to draw a parenthesis. I just didn't pick up the pen. So try to convert each of these into an exponential. Okay, so the first one, we take the base is 1.6. The exponent is 3, so that would give me 3 is log base 1.6 of w. In the second one, the base is e, so u, the exponent, is log base e of 25. And in the third, the base is b, so 5, the exponent, is log base b of 27. Now change these logarithmic statements into an exponential one. identify the base, and then whatever it's equal to is the desired exponent in the exponential. So log base b of 8 equals 3, so b to the third equals 8. Log base e of c is -2, so e to the -2 is c. And finally, log base 4 of 6 is w, so 4 to the w is 6. Okay, we identify the base and then use it as the base of the exponential. The thing that it's equal to is the exponent, and the thing that you are taking the log of is what this exponential is equal to. So can I find exact values of the following? In other words, if I say, what is log base 3 of 81? If it's something, then if I convert this to an exponential, I'd get 3 to what power is 81? So from my logarithmic, we convert it to an exponential and ask 3 to what power is 81? Well, 81 is 3 to the 4th. But now I have the same base on both sides, which means the exponents must be equal. So try to do the same thing for log base 5 of 125. 1 over 125, sorry. So 5 raised to what power equals 1 over 125? So convert this to an exponential. 5 to the y is 1 over 125. Find a common base. How about 5? Because 1 over 125 is 5 to the -3rd power. But now I have the same base, therefore I can say the exponents are equal, and that's my solution. Log base 5 of 1 over 125 is -3. And yes, of course, if you know how to plug these into your calculator, it will tell you the same thing, but now we know why it's true. So let's talk domain and range of logarithmic functions. Because they're inverses, the domain of the log function is the range of the exponential, that's positive numbers. But the range of the log is the domain of the exponential, that's all real numbers. Okay. So it exactly flops or switches domain and range of the original exponentials. Now, for an exponential, your domain was everything, but your range had to be positive. Now it's the reverse. For logs, your domain is positive, but your range isn't. So find the domain of each of the following. Just remember, any basic original logarithmic function, the domain is positive numbers. So for the first one, we need the input x plus 2 to be positive. So x needs to be bigger than -2. Okay. The second one, we need this input to be positive. Now I have a chapter 4 type problem. Where is this rational inequality satisfied? If you solve the rational inequality, it will be everything in between 5 and -5. We're not going to do every step out. By the way, this becomes very common in math. Solving where a rational equality is held, that was a whole previous section. If you need to practice that more, by all means do. Go back and view those videos, ask questions in office hours, do more practice problems. But it's quite common that something like that will now just be a step in a new problem. Can you solve this rational inequality? We presume you can do it at this point. So we presume you can get the answer is everything in between 5 and -5. Part C, the input is absolute value x. Where is that positive? Everywhere except 0. Remember, the domain for a log function does not include 0. It has to be a positive number. Okay, so here's a nice little summary. The domain, positive numbers. The range, everything. The x-intercept is 0, but there is no y-intercept. Remember, you're not allowed to plug in x equals 0, and this is exactly the reverse of the exponential. For the exponential, the y-intercept was 1 and there was no x-intercept, but because we're an inverse function, we switch the role of x and y. It's exactly reversed for logarithms. We don't have a horizontal asymptote of y equals 0. We switch x and y, so we have a vertical asymptote of x equals 0. A log function is decreasing if the base is less than 1 and increasing if the base is bigger than 1. And it has some certain points on it, and it's a nice smooth and continuous curve because it's the inverse of a nice smooth and continuous curve. So let's see the picture. So the blue is exponential. If a is less than 1, my exponential goes up to the left. And if I try to reflect it across the line y equals x, we end up with this curve right here. It has a vertical asymptote of x equals 0. Much more common is the one on the right where the base is bigger than 1. We'll see why that's true. Then you would generally have, here's your exponential, increasing to the right. It actually stays completely away from this line, in which case when you reflect it, you stay away from the line as well. So here's your generic log curve. It still has a vertical asymptote of x equals 0. Okay, so come on back for the next slide where we will discuss the natural log function, which is a very special and most common type of logarithm.